First, I talk about the schedule, then coverage, then question arrangement. Basically, these three things. If you have more to ask me, so then I will answer your questions. Yeah. All right. Yeah. So let's final exam. First, let's look at the school calendar. This is the school calendar for the summer semester. What? 8 weeks. And we mainly focus on the final portion, final exam. Yeah. You can see this final period starts from August 2nd, Wednesday. Okay. And we use this Thursday as our final test date. Okay. Then you can see August the 1st still in our regular semester field. Yes, period, right? August the 1st. Tuesday, still, it belongs to our regular semester. Regular class, that part, okay? That means this is our last class, last regular class. And in this one, I will do review for final. Okay, yeah, review for final. Okay, yeah. So most part, yeah, most part. Yeah. All right, so that's the first thing for you. Second thing, the coverage. Yeah. So one student asked me the coverage for the final. First thing, not accumulative. So after you focus, after the midterm, specifically, if I put the midterm, yeah, specifically, after module 3, part AB, yeah, because this part belongs to midterm, okay? Belongs to midterm. Yeah. So that means my questions mainly after this line, okay? Yeah. So here there is a line. So our final questions, after this line. Okay, all right. Yeah. So you focus on the new knowledge part. Yeah. All right, so that's the second question. Third question related to the question arrangement. Yeah, so we have some special arrangement. Yeah, I mentioned a little bit before, but this time I give you more information, more details. Question setting, okay, or format. Yeah, so, all right. Now I want to divide our whole set of questions. We have 25 questions. Whole 25 set of questions into 3 parts, not 2, 3 parts. Yeah. I have some reason for these 3 parts. All right. Part 1. Part 1, 10 questions. 10 questions. Remember, in one of my announcements, I told you I plan to use the first 10 questions of homework 2 as the quiz 4, right? Yeah, so homework 2, first 10 questions used for our quiz 4, because in that way we can save some time. Yeah, so we do not, yeah. The semester too short, we cannot do that many quizzes. Then the final also first 10 questions used for quiz 5. Okay, then this part you can see I take it out, use both places, but also that means I can assign to you earlier, not August 8th, because that 2 hours, you can get these 10 questions a few days before August 3rd. Yeah, it can work. Yeah, to your benefit. Okay, yeah. So a few days before, yeah, assigned, a few days before August 3rd, final test date. Okay, yeah, all right. So you can, do your work, okay? Study, spend your time, a lot of time, right? Yeah. Okay. Yeah. Yeah. But another thing, special thing I'll let you know. This set 10 questions I give you as a quiz type. So you submit it or not quite important. On the final day, you bring your answers, all right? After I pass your final test paper, you put your answers on the first 10 questions, all right? Save your time, okay? You already spent a few days study, work. Yeah, some students I know you have 2 classes. Yeah, probably a little hard for you. Yeah, yeah, but yeah. Sorry for those students. But for most students, you only have this class. Then you can have more time study to get better grade. Yeah, so that's to your benefit. Okay, yeah. So you just bring your answers. Yeah, put the answers. Save a lot of time. Then in the class that you only work on another 10 questions. Part 2, 10 questions. How about that? Okay. Part 2, 10 questions. These 10 questions, you can see, you need to solve them completely in the classroom. Yeah. So I want to see you really do your work. Yeah. I need to see. Okay. So you solve them in front of me. So yeah. So this part also important for me. You have 2 hours to complete it. Okay. 2 hours. Yeah. We start from 5:30 to 7:30. Okay. 5:30, 7:30 p.m. 2 hours. Okay. So our mainly to solve 10 questions. Reduce your load. Yeah. Question?
Will that still be open notes?
Yes. Open notes, open book, yeah, everything open. Yeah. Because I check your understanding. Yeah. Not your memory. Okay. Yeah. So you need to have good understanding, logic, reasoning, problem solving. Yeah. Problem solving. Okay. Yeah. And still the questions mainly based on homework assignment number 2, not brand new questions. Yeah. Typically not brand new questions. Related to, okay, partially related to homework 2 questions. Yeah, mainly, yeah, Yeah. So you know, because you have seen the relationship between the midterm and the homework 1. Yeah. Midterm, homework 1, final, homework 2, same relationship. Yeah. Then part 3. Part 3, 5 questions. Okay, 5 questions, I would say relatively challenging. All right. All right. Yep. And give you a little more times. Yeah. Let's say August 3rd, 4th, 5th. Okay. 3 days. How about that? 3rd, 4th, 5th. Yeah. 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 Here. Yeah. Because we're based on our official final period, right? Yeah. So here, based on this standard official final period. Yeah. So these 5 questions. Yeah. So you have August 3rd, 4th, and the 5th, 3 days. Yeah. Although 3rd, you need to worry about the, part 2, right? Yeah. But I make it available. On August 3rd. Okay. Yeah. So after you finish the test, maybe you take some rest, then you can work. Yeah. I know it's hard. Yeah. It's hard. Yeah. But we need to complete it. We need to complete our required work in this way. Yeah. Any question? Yeah. Now you can ask me a few questions.
Are we gonna still have 6 quizzes?
No. 5. Yeah. 5. No number 6. All right. Yeah. So the missing one, the 6th one, I just scaled it. Okay. So we have 5 quizzes. 5 quiz scores. 5 quiz scores. I drop your 2 lowest. Okay. I drop your 2 lowest. So you get 3 quiz scores, but I scaled it to 4. How about that? I multiply 4/3. I multiply by 4/3. I scaled it to 4 quizzes. Okay. Yeah. So we're still fitting our formula. We fit it in our formula calculation. Okay. All right. Your question? Yeah. Yes. Yeah. Right. Yeah. Yes. Yeah. So homework 1 midterm gives you idea how I made modification. Okay. Yeah. So you need to be very familiar with old questions. If you treat it as a brand new questions, then it could be hard. So if you connect to old questions, yep, that's our background. So we have a lot of background. So don't drop that part. Then new question built on top of that. Okay. Yeah. Then it won't be that hard. Yeah. Otherwise, if you just get a new person somewhere on the street, work on that question, that would be very hard because there is no background. Okay. How can get a homework 2 background? They don't. Then it's very hard. But we have a lot of background. Okay. Yeah. So that won't be too hard. Okay. But you need to make that connection. That's your responsibility. Okay. Not my responsibility. Okay. I won't tell you how to make the connection. Yeah. Other questions? Yeah. Other questions? Yeah. So that's, I saw some chat messages. Yeah, let me look at the chat messages, answer the questions from these students. Yeah, Mindy, yeah, confirm. Yeah, no, yes, yeah, you're allowed to use notes. Yeah, bring your note. Oh, I even allow you bring your computer, laptop, all right? Access notes, electronic material. You're not on paper. You don't need to print out, thick notes, paper. Yeah, but when you use computer, you cannot use search engine, all right? Yeah, do not use search engine, okay? Yeah. Oh, only our course materials. Download. Yeah, I'll print out. Test paper. Yeah, paper version. Yeah. I mean, I just use the Xerox machine. Yeah, that one. Okay, cool. Yeah, send.
I think they're having internet issues.
Yeah. All right, so I just try to process all your comments. Okay. Yeah, computer. All right. Yeah. Okay. Good. All right. And next, Jacob, get confused. Part 3 of the final. Able to do that beforehand, or do we need to do that yeah, not necessary. Not part 3. Yeah, 3 days. Yeah, 3 days. Yeah. Because challenging. I allow you to use a little more time after the. Yeah, correct. Online. Yes, online. Yeah. Okay. Reduce your pressure. Mainly the part 3. Reduce your pressure. Okay. Yeah. So you. Yeah. Try to. Yeah. So let me see more questions. Yeah. It looks no more big questions. Okay. Yeah. I will finish this part soon because we have a lot of material to cover today. Yeah. But this part also important. Yeah. Just let you know. All right, let's move to our, but I need to move a little fast. Yeah, I already spent near 30 minutes, so I need to do a little fast. All right, first I need to complete the quick sort. Yeah, just a few questions related to quick sort. So you need this part. D.6, best case efficiency of quick sort. So this part I like to move a little faster. Yeah. All right. Yeah. So first, let's study the best case. Under what situation we have the best case? Let's look at that. The most balanced partitioning. Yeah. The best case occurs when we have the most balanced partition. Okay? So the opposite situation, when most unbalanced situation occurs, you have the worst case. Just opposite. Okay? Here you have a good idea on it. Okay? So what's the most balanced partitioning? S region, L region, almost equal. Almost equal. Okay? The pivot element almost in the middle, yeah, and the corresponding recurrence relation is like this. Yeah. T, number of comparisons, T of 1, no comparison, T of 2, 1 comparison. Yeah. Then for the general N, so we use this kind of asymptotic notation here. Yeah. Actually, it may not be, may not be quite rigorous, yeah, but you know what's the meaning. Here you can replace this big theta omen by C times M for some constant C. Certain fixed constant, okay, to make it simpler. Yeah, all right. Yeah, now you can solve this recurrence relation, but here we do not use math to solve. We use computer science way, okay, not math way. So here we, based on our understanding, we will use the recurrence tree to solve. Last time I mentioned there is, one for merge sort recurrence tree there, but I want to save some time, so I didn't run that recurrence tree. Here we have a second chance. Yeah, we just run it once. Okay, yeah. Construct a recurrence tree. Here I just show you. I'll quickly show you. Idea is pretty simple. Yeah. Before we draw that recurrence tree, we want to figure out how many levels should we draw. Yeah. It's a binary tree, many levels. We need to stop at some point. The bottom level, we will use this inequality to estimate. And is between two adjacent power of 2. Power of 2, 2 adjacent. Yeah. So that's the case. Yeah. Because we can have this inequality, n over 2 to the k plus 1 greater or equal to 1/2 less than or equal to 1. Yeah. Well, when we split the length less than or equal to 1, we need to stop. That's the bottom level. We do not need to do another split in the middle. Yeah. This tells us we already reached this bottom case. Okay. All right. Yeah. Now the recurrence tree binary looks like this one. Okay. So each node, you can see each node, I put this non-recursion cost term. This is the constant. That's the cost we pay when we combine two subarrays. Yeah. Because recursion, we take care of recursion term by the remaining levels, right? Yeah, we will go many levels. Those levels, we take care of the recursion terms. Yeah. All right, so you can see each term, each node in this binary recursion tree, we only write the non-recursion terms. Okay, yeah. So in this one, so here you can see, so that's the tree. When we estimate the total cost, when we solve this problem, we need to accumulate all the non-recursion terms. Yeah. So in this tree, let's accumulate all the recursion terms. Okay, yeah. Level by level. How about level by level? Okay, top level CN, right? Yeah. And so top level, the same as CN. Second level, after accumulation, subtotal also CN, right? So you can see each level CN. And the bottom level also CN. Okay, yeah, that's easy. Then you add up all the levels, all those CN. How many CNs we can add? K plus 1 CNs. Because the top one corresponds to 2 to the 0th power, right? The second one corresponds, the denominator corresponds to 2 to the 1st. And this, the bottom level, 2 to the kth. Okay? Counting by reference. 0 superscript reference 1 from 0 through k. Consecutive. That means k plus 1 CN. Okay, yeah, k plus 1 CN. But we can drop that 1. Minor terms, we can drop. Okay, we can only keep the k. The k approximately log n. K approximately log n. Yeah. So we can get our estimate cost, big theta of n log n. Big theta of n log n. But that's for the best case. That's for the best case. Okay? Best case. Yeah. Best case, most balanced partitioning. All the levels, you will have the best case. And log n. Not the worst case. Not the worst case. Okay? Yeah. But before we look at the worst case, our next topic, we look at the worst case. Before we look at the worst case, average case analysis is far too hard to estimate. Because if we consider all the possibilities, too hard. Yeah, yeah, but the average case very close to this big theta n log n. Very close to. Yeah. Yeah. Slightly worse than the best case. A little worse. But how much worse? We don't know. Yeah. But by experiments, people do experiments and see pretty close. Based on the experiment data, very close to the best case. Okay, yeah. So that's the quick sort. Yeah. All right. Next, I like to. Oh. All right. Yeah. Average case efficiency. Yeah. So also this one. Here you just use it. Okay. Yeah. If I ask you what's the average case efficiency, you just use that expression directly. Okay. Directly. All right. Yeah. But one thing here, I want to remind you, yeah, at this point, one common mistake in your homework answers, some students use this formula directly. For example, when I ask you what's the minimum number of comparisons to sort 5-element array, so those students put in 5 in this formula. Then, round it up to get the answer. That won't be correct. Because this is asymptotic notation. Asymptotic. For large n, we have this. 5-element is a small n. So this formula won't be close. Won't be close. Okay? So when I ask you for relatively small n, so you should use the lower bound formula. Log base 2 n factorial ceiling function. That's our lower bound. Lower bound. No. Not asymptotic. You can see this lower bound formula, we do not use asymptotic notation. When you use asymptotic notation, you can only use for approximation when n is very large, not small. Not small. All right? Yeah. So because quite some students using asymptotic notation formula to get an answer. That's not conceptually, that's not right. Okay? Yeah. Just one thing I want to point out. Yeah. All right. So we finish this topic, but there is how to improve the performance. Yeah, that's another question. Yeah, because here, worst case occurs when you get most unbalanced data distribution after partitioning. So then people feel we can improve, we can avoid that kind of most unbalanced data distribution cases. Yeah. So do something, so improving the performance, do some work, do some little work. You cannot do too much work. If you do too much work, that means you will pay too much. So after you pay too much, you cannot save money, right? Think about this logic. You already pay a lot of money to get something improved. But that amount of money, you won't get 100% back. Okay, so actually you will lose some money. Yeah. Here the similar situation. We do some work before we do the partitioning. Yeah. Here, one is the randomization technique. Randomization. Yeah. So here I convey the idea. The idea is interesting. Yeah, but the result here may not be good, may not be better. You may not get a better solution. Yeah. All right. So what's the randomization technique? Use our current method, our standard method. We use the last element as the pivot, right? Yeah. Based on our current method, or the first or the last. Yeah. We have two options. Yeah. But no matter you use the first one or the last one, you may have some bias. Think about when you have ascending order array, descending order array, you have a lot of bias, right? Think about you apply it on ascending order array or descending order array, you get all unbalanced distribution. We don't like that. Okay? We want to avoid that. So your idea is we want to break the pattern because ascending order, descending order, they have strong pattern, right? Strong pattern. We want to break that pattern. How do you break that pattern? Here, simple method we call the randomization technique. So we don't choose the first one or last one. We choose one anywhere in the array, randomly select one and do swap operation with the last one. How about that? We select one element randomly, swap it with the last element of the first, then we run partition step. That randomization step, this idea is pretty good because we can break any given pattern. Any given pattern we can break. Okay? If you give me ascending order, descending order, we can break it easily. Think about that. Okay, all right. But for the result, people do a lot of experiments to do comparison. Yeah, actually, I assigned that experiment to my previous students before they did experiments. But result, this randomizing actually a little slower, cost a little slower. Because I asked them generate random data, so not ascending, descending. Yeah. So actually they do extra work, right? So you do randomization step, then you do partitioning, you do extra work. But the data you generate, actually the random data, you won't have ascending, descending patterns. So for that result, actually a little worse. Yeah, a little worse. I just let you know the whole picture like this. All right. Yeah. So we have to move to next topic. Okay. Yeah. All right. Yeah. Although there are several things we can do. Yeah. So here, yeah. But there is another one called the median of three. The same thing people get. The median of three. What's that? When you select pivot, you select arbitrary three elements and find a median, use that median as the pivot. But when you do that, you need to pay some cost here, right? You need to do three comparisons. You select the three random elements, three comparisons, swap, so you pay some cost. But as a result, you may not get a better performance because you pay too much here. So that's another similar situation. Yeah. So, but the idea also break the pattern, right? Yeah. We can break. We try to break the pattern in this way. Yeah. But this cost is higher than randomization, right? You need to do more work, higher than randomization. Yeah. Yeah. All right. So whatever it is, here I just let you know, but the result may not be good. So for that reason, most people just use the original quick sort. So no modification, just original quick sort. Yeah. All right, yeah, so yeah. All right, so let me start this topic. So let's move to our new topic. Yeah. All right. Now I want to move to module 5. All right. Yeah. So let me look at the time. Yeah. I only have about half an hour. Yeah. It's hard to complete. Yeah. Anyway, let's just heap sort. This is our last sorting algorithm, heap sort. But here we focus on advanced data structure. Okay, yeah, it's quite special. Yeah, our previous sorts, the data structure just plain arrays. Yeah. Nothing special. But here, a little special. We will make our data structure with some very special properties. While we do that, you will see we try to address some interesting requirements, special requirements. All right, introduction. Yeah, the same sorting algorithm, but this time let's consider we need some special requirements. The first, worst case efficiency should be under control, not very bad, should be this in this category, big theta of n log n. Yeah. Currently, we have one of our sorts with this property. That's the merge sort. That's the merge sort has this property. Okay. Yeah. So our new sort, we also want this property. Okay. No bottleneck. Yeah. Very bad worst case, we may treat it as some bottleneck. Okay, so we want to avoid it. All right. First requirement. Second requirement, it should be in place. So here, let me explain this in place meaning. Yeah, this in place. Yeah. All right. It is different from our array elements in place. We have that concept, right? Yeah. Array elements, some certain element is in place. That's one concept. But here is the algorithm in place. Some algorithm. What do you mean? So algorithm in place, slightly different. Yeah. So the main requirement for this type of algorithm is, oh, sorry. Yeah. Yeah. The main requirement for this type of special algorithm is, we know last time I mentioned when we implement some algorithm, we need to use extra space, right? We need to use extra space. Extra space other than input output. Input output, you have to store your input output, right? So that's what we treat as the, the standard. Yeah. Nobody can save that amount of space. So that's the, standard space. But other than the standard space, you also need some extra space, right? Extra space could be large, could be small, right? Yeah, think about that. So, but for in place, we want to make our extra space use big theta of 1 constant. In this category, Then, if your algorithm only use extra space in this category, we call it in place algorithm. Okay. Otherwise, if you use too much extra space, we do not call it in place. You know, this is a good property. Yeah, right? Use less extra space. Yeah. So this is a good property. So that's why our requirement number 2, we want to have it. Yeah. It does not use too much extra resource. Yeah. But our merge sort, we do not have this in-place property. Our merge sort, remember when you merge, you need to copy elements, right? You have a destination array you need to put in place. But it's hard to avoid that auxiliary array. It's hard. We don't know how to avoid it. For merge sort. Yeah. Yeah. So merge sort is not in place. Yeah. Not in place. Yeah. All right. So here we need it in place. But so here, because we are at this point, I also want to make some comments for quicksort. Quicksort, for each partitioning, each partition step, it's in place. Yeah. Because we only have one extra space, right? But if we look at the whole quicksort, it is very hard to say it's in place because it use recursion. When you use recursion, you think about when there is a recursion. When you use recursion, you need to use a stack to implement, right? Your stack could be pretty deep. Your stack uses a lot of resource, right? You cannot say the stack, that amount of is under control, under constant. The stack memory used not in big data of 1, right? Yeah. So that's extra space used. So we cannot say that's completely in place. It looks in place, but actually it's not. It looks in place, but there is some hidden thing you cannot see, use extra space. Yeah, so that's the quick sort. Merge sort, we also use recursion. When you use recursion, you may not get in place sorting algorithm. Yeah. But here, this one, to avoid stack, we do not use recursion. We use for loop. We use for loop. There is no stack. Yeah. We use for loop, run from beginning to end. Then we know how much extra space we use. Okay. So here you can see that's the main difference. Yeah. All right. So the second requirement. Third requirement, maintain dynamic data efficiently. Yeah, quite special. Yeah. This requirement, in some real-world applications, it is useful. So what is dynamic data? Data comes in and goes, right? In and out frequently. Think about that. We keep changing our data. Sometimes we insert new data items. Sometimes we delete data items. So your data structure should support efficient operation on adding new data and the data deletion. When you add new data, you need to insert in some special location, but the insertion cost should not be very high. Should not be very high. Okay, yeah. So, yeah, specifically, what do you mean? Done. So do you have something in your mind for the efficiency, handling dynamic data? Yeah. Here we have, let's look at the insertion. When you insert a new data, if you if your operation is big theta of n, then it's not efficient. We treat as not efficient. Too much work. So we like to have big theta of log n. Log base 2, log n here. Yeah. If we can get the maintaining cost in that big theta of log n, then we feel pretty good. Yep. So we are satisfied. Yep. So here you can see what's the difference between these two. Big theta of n corresponds to linear search. Linear search, big theta of n. Yep. So in ZER, you find location by linear search. Big theta of log n, binary search. You find the right location by binary search. Yep. So we feel we want to have the binary search type of efficiency, not linear search type of efficiency. So that's our third requirement. So the new sorting algorithm should have all these three properties. Then we feel for certain type of applications, we like to use this kind of sort. All right, yeah. Let's see how to get it. Question, idea. So we need so at the beginning we need to design a new data structure. Okay, we need to do a little more work. In our previous sorts, we do not need to design data structure. We just bring array, use that as data structure directly. Here we need to do some design work in our data structure. And this, in order to get a binary search efficiency, big theta of log n, we like to get a binary tree structure, right? If our data structure has the binary tree property, then we can find the right location quickly by the binary tree, big theta of log n. Yeah. So we want to connect to the binary tree structure, for our new data structure. So now the design details, how to make it happen. We want to make it as simple as possible. Make data structure not too complicated. Too complicated, the cost will be high. Make it as simple as possible. All right, so here are the candidates. Let's try to find some candidates. All right, because when we look at a binary tree structure, you need to address parent-child relationship, right? Which node is a parent node? Which one is child node? You need to address that parent-child relationship in your tree, right? In our old array, we do not have the parent-child relationship represented. Here, this time we need to represent parent-child relationship. So we need to select candidates for the underlying data structure. So your data structure should support parent-child relationship. All right. So one is array. We're familiar with array, so we want to try, can we do it in an array? So that's one of the candidates. Another linked list. Linked list. In CS3250, you learn a linked list, right? Much harder, much more complicated than array, because you need to use pointers to point to different nodes. But when you point to different nodes, you can address parent-child relationship, right? Parent node, child node, left child, right child. You can use pointers, right? Yeah. But yeah, most people may not feel comfortable using pointers. Okay? Yeah. So most of you, actually, I do not like. I want to avoid, if it's possible, I like to avoid using pointers. Okay? Yeah. All right. So here, array is simpler. Yeah, we prefer to use array. In array, we do not use pointers. Yeah. Yeah. The question is, can we use an array directly? Something is missing in an array. Yeah. Yeah. So in order to maintain dynamic data efficiently, the binary tree structure, we cannot use it directly because no parent-child relationship, right? So we need to do some extra work. So the idea is, can we modify array? We don't want to throw away. If we throw away, we have to use linked list. It's too complicated. So we want to try, can we modify array a little bit to allow us to address that parent-child relationship? If we can, that's a good solution. No pointers. Yeah. All right. So let's modify it. So our next step, we want to build binary tree structure in an array. So this time you can see we build a binary tree structure inside an array. That's something new without using pointers. Because in an array, you have no chance to use pointers. Right? You don't want to use pointers inside an array. Okay? Yeah. All right. How to modify the array? Okay. All right, so here let's consider the data stored in an array. So here we want to remember, we want to address the parent-child relationship. So let's consider all the data items stored in this array based on locations, right? In array, we have locations, array indexes to give us locations of the data. Okay. All right. All right. So if we assume the data is sorted, the current data is sorted, yeah, because at the beginning we can do initial sorting. Yeah. When new data comes in, we insert it in a sorted array, but we want to do binary insertion, binary search type insertion, not linear search type insertion, too slow. Binary search, we have sorted the data, so we can do binary search. We want to do that. Okay, yeah. Yeah. So the data comes in, if you add at the end of the array, then it's not ordered, right? Because in array, if you add end of the array, it's not ordered. Okay? Yeah. So you have to put it somewhere, some interior location. So usually interior location. Yeah. All right. So you want to make it order in some efficient way. So you need to consider the insertion, not in the linear search. Yeah. So this is the linear way. Okay. This is the linear way. Sorry, linear way. We don't like it. So our goal, we want this binary search way. Okay, yeah, this is our goal. Okay, all right. So now, so let's look at the insertion. Yeah, linear search, binary search. Yeah. So here, in order to make our data structure to support binary search, so we need to build a binary tree. Okay. When we have a binary tree, then we can do the search based on the binary tree structure. Okay, yeah. So the question, yeah. Question here. We need to add some new property in the array to support the binary search. All right. Yeah, still array is the underlying data holder. We still use array to store the data, but we can control the locations of the data. We can have some fast control on data locations. That's something we can do more than we can do before. In the old ways, we do not have a lot of control related to parent-child relationship. We don't have that. Yeah. Here we need to add more control related to parent-child relationship. We organize the array elements in different levels, addressing parent-child relationship. Then we can move elements around between different levels. That's the new operation we can do on an array. All right. So the detail, binary tree structure in array, details. Let me see. Now, I still have 10-something minutes. Good. All right. Binary tree structure in array. All right. How to get that? Yes, actually, it's pretty simple, not too hard. Yeah. How to build a binary tree inside an array? We introduced the heap data structure this time. So that special data structure. We call it heap data structure. So the properties we need use an array as underlying storage object. First, two, near complete binary tree. So this it's not a complete, because if you want to get a complete binary tree, the number of nodes should be n equals power of 2 minus 1. Then you get a complete binary tree. This many nodes, you can get a binary tree. But usually our n cannot be represented in this special form. So we won't get a complete binary tree, but it's near complete binary tree. Here the question, what do you mean the near complete binary tree? All right, so here the description is, so we have a binary tree, then you look at all levels are full except the bottom level. Bottom level not necessarily full, but other than the bottom level, all the other levels all full. Okay? Yeah. So you put as many nodes as possible in all other levels, but bottom level, just the remainder, right? Yeah. So remaining. So usually you cannot make it a full. Yeah. So we call that kind of complete, near complete binary tree. Yeah. Here, let me draw a diagram. Yeah. So you can see this one, all levels are full except the bottom level. The bottom level not full. Yeah, it's fine. Yeah. Yeah. So we pack the elements all level by level, make the current level full, but the last one we just put the remaining elements in the last bottom level. Okay. Yeah. Only the bottom level may not be filled. Yeah. So we call this kind of binary tree as near complete binary tree. Okay, yeah, all right. Yeah, and sufficient space for dynamic data. Yeah, here the property. Yeah, because dynamic data at the beginning you may not be able to predict, right? You use an array. Do you remember when you need to create an array? You need to declare the size of the array, right? The array, you have to declare size of the array at the beginning. But do you have an idea how large is the size at the beginning, because your data is dynamic. It's hard to predict how many data items. So you just at the beginning, you can make your first assignment size, because later if you have more data items than the array size, array locations, you can create a new larger array and copy your data to that new larger array and continue. Now, you need to do that kind of work, move your data. Yeah, because old array too small, you need to move it to a new array. But that kind of operation, very expensive. Think about that. That operation is expensive. But you have to do it. Okay? Yeah, so here you have to do it. Certain relationship among nodes. This is the most important property we need to address. Number 4. How to address the parent-child relationship. Yeah. Other things, relatively easy. Yeah, but this number 4, we need to do some special treatment. How much space is efficient? Yeah, so I just give you an idea. At the beginning, hard to know, but we can make some reasonable array size first. Yes, it's some reasonable array size. Okay, yeah, yeah, all right. Certain amount of space initially, but after we keep adding new data, we need to monitor the remaining locations in our array. At some point, your array will be filled quickly. You need to prepare for a new larger array to copy your data. Okay, yeah. So you set some threshold. When a threshold is reached, a new array with larger size is created. And you copy the data to the new array. Okay, yeah. So in that way, you can get a larger storage data structure for the new array. Okay, all right. So usually it is very expensive to copy large data. Then think about when you copy a large array from old one to new one, it takes a lot of time. Okay? Think about you copy millions of elements. That would be very slow. Okay? So then if your program implement in that way, then your users, your customers will notice significant delay. At this point, data copy at this particular point, there is a long delay. Your customers won't be happy. This is a big bottleneck. Okay? Your implementation, you have a big bottleneck. So you should remove that bottleneck. So make your customer happy. So no delay. Yeah. Every place, running very smooth. No significant delay. Yeah. So you need to fix this problem in like this. Here, we have a big bottleneck. This peak, yeah. Let's say the waiting time, okay? Your customer, the waiting time, your customer has to wait in this bottleneck, this peak time, okay? Let's say a few seconds. A few seconds already very slow, okay? 3 to 5 seconds, that's too slow, okay? You want to avoid that. No such long delay, 3 to 5 seconds, okay? Yeah. So how to avoid it? The idea, so here I'm only talk about idea, okay? The idea is, can we spread this, because here, you need to do this amount of work, right? The reason it makes long delay, you need to do a lot of work here. Can we spread the workload on a long period of time? How about that? Okay, so the diagram I like to draw this way. Okay, because we can detect before the array is failed. Yeah, there is still some time before that. We do the copy work. We create a new array. We do copy work in a relatively long period of time. How about that? Okay, but then we spread the load. So every time we do not do too many copies, we just do a few copies. Yeah, but we spread on a relatively long period of time. So your customer won't notice. Yeah. So it is a little slower than non-copy part. That's the non-copy part. Here, the copy part, small copy part, is slower than the non-copy part, but just it's not significant. Your customer won't notice the difference. Yeah. A few milliseconds. Think about the difference. A few milliseconds slower, your customer won't notice that. But you spread in a long period of time. Let's say, hold 5 minutes to 10 minutes time. Think about that long. Okay, you spread 5 minutes to 10 minutes, that long period. Spread a copy load. Then your customer won't notice that. Okay, no long delay. Yeah. In this way, you can solve this bottleneck problem. Okay, you switch to a larger array, you make the data copy, but no long delay. How about this idea? Okay, yeah. So here we do not do implementation. You need to write the code. When you do implement, you need to write the code. But here, just we have this idea first. All right, let's move to the next topic. Heap property, 8.3. Let me see how much time. Yeah, I don't have much time. Yeah, I need to leave it. Yeah, the second half. The second half, I like to give you about 40 minutes for your homework 2 questions. So I can